Have you ever built a really powerful machine learning model, one that's right most of the time, but then suddenly makes a simple, obvious mistake? It's like watching a grandmaster in chess completely forget how a pawn moves.
So why does this happen? Well, it's because any single model, no matter how complex, has its own unique blind spots and weaknesses. It only sees the world from one perspective. The real question is, how do we build something that's more reliable than any one of its parts?
In this explainer, we're going to cover why a single model can be flawed, the power of using a group of models, 3 main strategies for doing that, and where you'll see this in the real world. By the end, you'll understand exactly why combining models leads to more accurate and robust systems.
Okay, let's start with the core problem. Relying on just one model is what I like to call the lone genius problem. You might have an incredibly smart expert, but even a genius has biases and gaps in their knowledge.
A single model is often stuck in something called the bias-variance trade-off. If it has high bias, it's too simple and misses important patterns. But if it has high variance, it's too complex and ends up memorizing the noise in your training data, which means it won't generalize well. Ensembles are designed to find a better balance, reducing the risk of either of these problems.
So what's the solution to this lone genius problem? Well, instead of asking one expert for advice, you assemble a whole committee of them. This is the big idea behind ensemble methods. It turns out that a diverse group of opinions is almost always better than a single one.
And that's exactly what we do in machine learning. It's formally called ensemble learning. The goal isn't just to average out a bunch of guesses. It's about strategically combining the predictions from multiple models to create a single superior result.
Think about how a committee works. If one model makes a strange error, the others are likely to disagree and outvote it. Their individual mistakes, which are often random, tend to cancel each other out, but their correct insights reinforce one another. This is the wisdom of the crowd, just applied to algorithms.
All right, so we agree that building a team of models is a good idea. But how do you actually do it? Well, there are 3 main strategies, and each one builds the team in a slightly different way.
First up is bagging. You can think of this as the independent opinions approach. We create lots of slightly different versions of our training data, and we give one to each model. They all train independently, in parallel, and then they come together at the end to vote on the final answer. It's a very democratic process that makes the final prediction much more stable.
Next, we have boosting. This is the sequential learning strategy. Instead of training in parallel, the models train one after another in a sequence. We start with the simple model. It makes some mistakes. Then the second model is trained specifically to fix the errors that the first model made. The third model fixes the errors of the first 2, and so on. The team gets progressively stronger by learning from its past mistakes.
And our third strategy is stacking. I like to think of this as the expert manager approach. Here, you start by training a diverse group of models, maybe a decision tree, a support vector machine, and a k-nearest neighbors model, all on the same data. These are your specialists.
Then you train a final model on top of them. This is the meta model, and its only job is to learn from the predictions of the specialists. It essentially acts like a manager, figuring out which specialist to trust in different situations to make the best possible final decision.
So to quickly summarize the 3, bagging uses a parallel process to reduce variance, and its most famous example is the random forest algorithm. Boosting uses a sequential process to reduce bias, and that's where you find algorithms like XGBoost. And finally, stacking uses a hierarchical process simply to improve overall predictions.
Okay, that's the theory. But let's talk about where you'll actually see these methods being used in practice.
You will run into these names all the time. Random forest is the classic example of bagging. AdaBoost and gradient boosting are foundational, and XGBoost is a super optimized version of boosting that has absolutely dominated data science competitions for years because it's just so powerful and fast.
And their impact is massive. In finance, for example, a bank might use an ensemble to decide whether to approve a loan. One model in the committee might focus on income history, another on past loan performance, and a third on spending habits. The ensemble combines these different expert views to get a much more reliable prediction than any single model could.
Here's the most important takeaway for practitioners. When you are working with structured tabular data, the kind you find in spreadsheets and databases, these ensemble methods aren't just an option. They are very often the industry standard.
So, to wrap it all up in a single sentence, ensemble methods combine multiple models to create one final prediction that is far more powerful and reliable. And if you remember just one thing, let it be this. In machine learning, just like in real life, A diverse team of models almost always outperforms a single star performer.